Well, now it's time to take what we've learned in the applications for quantitative methods, confidence intervals and means and all of that. We're going to apply it to hypothesis testing. So hypothesis testing, that's just our scientific method, right? We state a hypothesis. We've got a relationship to be tested. And then we figure out a test statistic that we're going to use to test this hypothesis. And then we specify our level of significance, how confident we want to be. And then we state the decision rule. And once we've done that, then we can collect the sample, calculate the test statistic, evaluate that test statistic, and make a decision about whether we're going to reject the hypothesis or not reject the hypothesis. We never prove a hypothesis. We just fail to reject it. And then we make a decision, an economic decision, based on the test results. So we've got our null hypothesis and our alternative hypothesis. And so the null hypothesis, that's the one we're testing. And it must contain the equal sign. I can't emphasize this enough. Now it says in the CFA curriculum and other places, they say that's the one that researcher wants to reject. Well, you can get a little confused with that, but always stick with this. The null has to be equal to, greater than or equal to, or less than or equal to. And then the alternative is just the other side of that. So in general, it's what the researcher would like to conclude. And that's the conclusion we'll draw if we're able to reject the null hypothesis. Now, our hypothesis can be a two-tailed test or a one-tailed test. Here we've got a diagram illustrating a two-tailed test. Now notice that 95% in the middle, that looks a lot like a confidence interval. And then we've got 2.5% in each tail. So our critical values there are 1.96 standard deviations, either side of the mean here. So in this example, we've got a null hypothesis that the mean is 0. The alternative is simply not equal to 0. So if 0 is right here, when are we going to reject the null hypothesis? We're going to reject the null hypothesis if we get a value that's very far away from 0. When I say very far away, more than the number of standard deviations or standard errors that we've got in that 95% confidence interval. So if we get something around 0, we'll fail to reject the null. If we get something that is statistically significant away from 0, then we'll reject, either too high or too low. So anything out here in the tails, we'd reject the hypothesis that the mean is actually 0. Other times we might have a one-tailed test. Consider a null hypothesis that the mean is greater than or equal to 0 versus an alternative hypothesis that the mean is less than 0. Or another one-tailed test would be less than or equal to versus greater than 0. So for this one right here, when are we going to reject that? Well, even if we got a value clear down here, we're not going to reject that the mean is less than or equal to 0. Fine. The only time we're going to reject with this one-tailed test that mean is less than or equal to 0 is if we get a high test statistic. And if we want 5% in this tail, notice we've got no left-hand tail. So with 5% out here, our critical value there is 1.645, or sometimes we say 1.65 standard errors or standard deviations above the mean. Remember that 1.65 was our 90% confidence interval. We said 90% in the middle, 5% in each tail. So that's why we're using this for our one-tailed test with 5% out here in the right-hand tail. And the significance of the test is that 5%. The significance level of a test tells us the probability of rejecting the null when it's actually true. So given this distribution, 5% of the time, we're going to get values out here, even if the mean is actually 0, or in this case, even if the mean is actually less than or equal to 0, we could get 5% of the time we'd reject it incorrectly. And so that's our significance level. So a test statistic is calculated from the sample data, and then we compare it to the critical value to test the null hypothesis. If that test statistic exceeds the critical value, or is outside the critical values, then we're going to reject the null hypothesis. So these critical values, you can see, are very closely tied to what we did in establishing confidence intervals. Now, there's two types of errors we can make in hypothesis tests. A type 1 error is rejecting the null hypothesis when it's actually true. And that's the significance level of the test is the same as the probability of a type 1 error. A type 2 error, on the other hand, is failing to reject the null hypothesis when it is in fact false. And we define the power of a test as 1 minus the probability of a type 2 error, or 1 minus the probability of failing to reject a null hypothesis when it's false. And there's a trade-off between those two. You might think of a jury trial. We say, well, defendants are innocent until proven guilty. And we might establish the rules of evidence so it's very hard to convict an innocent person. And that would reduce your probability of a type 1 error, rejecting innocence when in fact they're innocent. But the other side of that is if we make those rules of evidence strong to reduce this type 1 error, we're going to increase the probability of a type 2 error, that is, failing to convict a guilty person. So if a hypothesized mean falls outside the confidence interval for the population mean, that's the rejection region. So consider an example. Mean daily returns on a portfolio over a 250-day period, we're working with the mean here, has been 0.1%, and the sample standard deviation is 0.25%. Determine whether the mean daily return is different from 0, that is not equal to 0, using a 95% confidence interval and a hypothesis test, therefore, that has a 5% significance level, 5% in the tails. So our standard error for our sample size is the standard deviation of 0.25% divided by the square root of 250. So our standard error is 0.0158%. Our 95% confidence interval is 1.96 standard errors either side of the mean. So there's our confidence interval there, 0.069% to 0.131%. So our hypothesized mean of 0 falls outside this confidence interval. So we can reject that. So our hypothesis test, mu equals 0, versus the alternative, the mean's not equal to 0. We have a large sample size, so we can use a z-statistic. Sample size is 250. And here's our z-statistic. How far are we from the hypothesized mean? Well, our sample mean was 0.1%, so we're 0.1% away. Now, is that far enough away to reject the null that mu equals 0? Well, that depends on the distribution. So we measure how many standard errors are we from 0, and it turns out we're a long way from 0. We're 6.33 standard errors away from 0. So that's way out in the positive tail. So here's a graphical representation of this hypothesis test. Hypothesis, mu is 0. We're going to reject if we get a test statistic too far. Well, what's too far? Well, anything more than 1.96 standard errors above 0 or minus 1.9 standard errors below 0 is our rejection region. And our test statistic, 6.33, is way out here off the charts. So we're certainly going to reject, with a high level of confidence, the hypothesis that the mean is actually equal to 0.